Okay, today we'll see about protection of alternators. Okay, now let us see protection of alternators. The generator units are special device, a very large one, and they are relatively few in number. That, for example, in Ethiopia, there are some generation stations. For example, Tanabalas is one of the generation station, and Tanabalas was the largest one before 5 or 6 years. So Tanabalas may generate 460 megawatts, but there are only 4 generators. In the same manner, Takaze, Awash, and such like generators have a few numbers. So generally, generators are few in numbers and they are higher individual cost than when you compare the other equipment. Most of the equipment they are more costly than most of the equipment. So it is desirable and necessary to provide protection to cover the wide range of faults which may occur in these modern generating plants. Some of the faults which may occur on the generators are, for example, it may be failure of prime mover, it may be failure of field, over current, over speed, over voltage, unbalanced loading, and the last one is the last one, but not the least one, is stator winding fault. Now let us see failure of prime mover. When the input to the prime mover fails, the alternator runs a synchronous motor and draws some current from the supply system. This is called motoring condition or inverted running. That means it converts from generator state to motor state. Now, it may be defined into different types of generator. For example, in case of turbo alternators, the failure of steam supply may cause inverted running, and if the steam supply is gradually restored, the alternator will pick up loads without any disturbance of the system. So, if the steam failure is likely to be prolonged, the machine can be safely isolated by the control room attendants instead of other automatic protection. Due to this condition is relatively harmless. Therefore, automatic protection is not required for failure of prime mover in turbo generators. When it's in case of hydro generator, protection against inverted running is achieved by providing mechanical device on the water here. So when the water fails drop to an insufficient rate to maintain the electrical output, the alternator is disconnected from the supply system. So for this case also, electrical protection is not necessary. When you see diesel engine driver alternators, when the running is inverted, draw considerable amount of power from the supply system, and it's usual practice to provide protection against motoring in order to avoid damage to possible mechanical surgery. So this is achieved by applying a reverse power relay to alternators, which may isolate the latter during their motoring actions. The second failure of alternator is failure of field. So the chance of field failure of alternators are undoubtedly very, very, very rare. Even if it does occur, no immediate damage will be caused by permitting the alternator to run without a field for a short period of time. So it is sufficient to rely on the control room attendant to disconnect the fault generators manually from the system bus. So for this failure of field also, there is no need of automatic protection against this fault. The third failure or the third fault of generator will become overcurrent. Its occur mainly due to partial breakdown of winding insulation or due to overloading of the supply system. That means when winding insulation is become less, there will be contact on that time. there will be overcurrent. Overcurrent protection for the alternator is considered unnecessary because of the following two reasons. The first one, modern tendencies to design alternator with very high values of internal impedance of the generator, so they will stand a complete short circuit as their terminal for sufficient time without severe overheating. That means due to that resistance or internal impedance. On the other occurrence of overload, the alternator can be disconnected manually now, so there is no need of automatic protection. The second reason will be the disadvantage of using overload protection for the alternator is that such protection may disconnect the alternator from the power plant bus on the account of some momentary trouble outside the plant, and therefore they interfere with the quantity of the electrical service. The other fault, or the fourth one, is overspeed. The chief cause of overspeed is the sudden loss of all or major parts of the load on the alternator. For example, in typical case, if Bardar substation fails, if Bardar substation fails, in that time there is a great problem for our electrical system. So in that sudden loss of Bardar substation, the overspeed maybe happen on generation stations, enablers, and like that. Modern alternators are usually provided with mechanical centrifugal device mounted on their driving shaft to strip the main valve of the prime mover when the dangerous overspeed occurs. The other one is overvoltage. The field excitation system of modern alternator is so designed that overvoltage condition at normal running speeds cannot occur. However, overvoltage in the alternator occurs when the speed of the prime mover increases due to sudden loss of alternators. When there is a sudden loss in substation, as I told you, for example, the sudden loss of Bardar substation may increase the overspeed. Overspeed by itself may cause for overvoltage. So there are different cases for different generators regarding about overvoltage. For example, in case of steam turbine drive alternator, the control governors are very sensitive to speed variations. Therefore, overvoltage protection is not provided on turbo alternators. In case of hydro generator, there may be some damages. The overvoltage may damage some insulations. So therefore, usual practice to provide overvoltage protection on hydro generators. And the sixth fault of the generator will be unbalancing loading. Unbalancing loading means that there are different phase current in the alternator. Unbalanced loading arrives from faults to earth or faults between phase on the circuit external to the alternator. So the unbalanced currents, if allowed to persist, may either severely burn the mechanical fixing of the rotor core, or they will damage the field winding. So this unbalancing load is several types of faults. So we must give automatic protection for unbalanced loading. Now let us see the protection mechanism. Under normal operating conditions, equal current flows through the different phases of the alternator, and their algebraic sum is 0. Therefore, under normal condition, the sum of current is 0, so there is no any algebraic sum on balanced system. Therefore, the sum of the currents flowing in the secondary is also 0. No current flows through the operating coil of the relay. However, if unbalancing occurs, the current induced in the secondary will be different, and the result of those current will flow through the relay. So the sum of the current may not be 0. So the operation of the relay will trip the circuit breaker to disconnect the alternators from the system. This is one of the protection mechanism of unbalancing system. So here is the generator alternator winding. Generator or alternator winding. Here is the ground. So if the system is balanced, the sum of the current in those cities, that means the sum of the current of phase R, Y, and B, E becomes zero if the system is balanced. If some problem is happen, the sum of the three systems may not be zero because they are totally unbalanced. If the systems are unbalanced, there is some current, sum of current may differ from zero, so there is a current which passes through the relay coil. In that time, if this current is equal to or greater than the pickup current of the relay will trip the circuit breaker. So they will give a signal to trip the circuit. That means if the relay is energized or operate, the circuit breaker will trip the circuit from this fault. The other fault of the generator, the seventh one, is stator winding fault. Stator winding faults. Those faults occur mainly due to the insulation failure of stator winding. The main types of stator winding faults in the order of importance are fault between phase and ground, fault between phases, and inter-turn faults involving inter-turn faults involving turns of the same phase winding. Now let us see those three types of faults in stator winding fault. Stator winding faults are the most dangerous, and they are likely to cause considerable damage to expensive machineries. That is very because this stator winding in most generators are found on the external part of the generator. They will going to the substation or the bus bars. So this is very critical for generator faults. So automatic protection is absolutely necessary to clear such faults in the quickest possible time in order to minimize the extent of the damage of the generator as well as damage of generator as well as the substations. So if the stator winding fault is not cleared quickly, it may lead to burning of stator coils. If there is a burning of stator coils, totally we cannot generate any power, we can totally lose the generation stations, and the other will lead to burning and welding up of stator laminations. If the stator lamination is totally damaged, hopefully we can bounce the generator and another place. So this is very, very critical issue. So it may suffer for different problems. The other thing, differential protection of alternator. If this stator winding failure is several types of fault, so there is it's required some protection mechanism. One of the protection mechanism of the generator stator winding is differential protection. So what mean differential protection of the alternator? This system of protection, current and the two ends of the protection are compared before and after generation. So at the ground side and at the load side, we'll compare the two currents. So when we compare the two currents, if they are the same, that's a normal condition. If there is a difference between the ground side and the load side, there is a problem. So under normal conditions, those currents are equal, but may become unequal on the occurrence of the fault in the protection side. That fault may be line to ground fault, it may be line to line fault, or it may be line to ground fault, or other types of fault. By any means, if the fault is higher, these currents cannot be equal. So the difference of the current under fault condition is arranged to pass through the operating coil of the relay. So the relay then close its contact to isolate the protection from the system. This form of protection also is known as multiplied circulation current. This multiplied is the name of the person who invented this differential protection of alternator. Now this is the schematic arrangement of the differential protection or multiplied circulation current principle. Here is the ground. So this arcing resistance for that ground, and those three ground side terminal of the generator are connected each other, and there is cities on this group of city, let's call it CT1. So CT1 for RYB phases, and this is the alternators. Now those are the fault, different type of faults. We'll return back on the faults, and this the other group, or the load side group of the current transformers. We call it CT2, and so those two cities, CT1 group and CT2 group, is connected by some wire. This wire is called pilot wire or pilot cables, and the terminal of this pilot wire at the middle of the two cities are connected in a star way. They are connected in a star connection, as you can see here. They are connected in a star connection, and this star there is one common wire, which is the fourth pilot wire, and this also connects to ground, or the neutral one. This is the neutral wire for the two. So the secondary part of the seats are connected inside. So this is the relays, relay 1, relay 2, and relay 3. Those relays are regarding with this phases. For example, relay 1 is for phase R, relay 2 is for phase Y, and relay 3 is for phase B. So there is also a tripping coil, or a relay coil is connected to each other in some conditions, and both three are connected together, and they'll give a signal to the circuit breakers. Now, differential protection of alternator principles. Let us see. Identical current transform pairs, CT1 and CT2, are placed on the either side of each phase of the stator winding. So the secondary of each set of the current are connected in a star, as I show in this diagram. Yeah, they are connected in a star way. And the two neutral points and the corresponding terminal of the two star groups being connected together by means of 4-core pilot cable. This one you can see here, and you can see here they are connected into in a star connection with the fourth pilot wire, which is called neutral wire. Thus, there is an independent path for the current circulating in each pair of current transformer and the corresponding pilot wire. Now, what will be the operation? Let me see in simplified manner. This is a simplified version of the previous diagram. This diagram. This is when you simplify, you can simplify in this way. So, under normal operating condition, the current at both end of each winding will be equal. This one and this one equal, and hence the current in the secondary of the cities connected in phase will also be equal. You can see here. You can see here that so the two cities, CT1 and CT2, are equal. So there is no any. If this one is equal to this one, there is no any current which may pass through this relay coil R1. And this one, if this one and these ones are equal, there is no any current which pass through this R2 or relay 2. So therefore, there is balanced circulating current in the pilot wires, and no current flows through the operating coil. That means corresponding relay coil R1, R2, R3 of the relay. When an earth fault or phase-to-phase fault occurs, this condition no longer hold good, and the differential current flows through the relay circuit operators and the relay to trip the circuit breaker. If the fault is happened, for example, somewhere here, around here, so this current is much greater than this current. So there is no this current may be zero approximately. So the rest current will flow across this line, or the two currents cannot be equal. The CT1 current cannot be equal to the CT2 current. So there is some current which pass through across R1. When an earth fault or phase-to-phase fault occurs, this condition no longer hold good, and differential current good, and the differential current flows through the relay circuit operates the relay to trip the circuit breaker. So if CT1 and C2 are not equal, that means due to the ground trial fault or line-to-line fault, so there will be some current which pass through across R1. that R1 means in relay coil 1. So if the current passes in this R1 and this current is greater than or equal to the pickup current of the relay 1, the relay 1 will operate. So they will operate and they will give signal to the circuit breaker, and then the circuit breaker will trip the fault system from the cage 1. So the relay circuit is so arranged that it is energizing causes opening of the circuit breaker connecting the alternator to busbar and opening of the field circuit of the alternator. So the relays will operate those two critical points. Okay, it is a prevailing practice to mount current transformers CT1 in the neutral connection, usually in alternator pilot, and current transformer CT2 in the switchgear equipment. In some cases, the alternator is located at considerable distance from the switchgear, maybe far from the switchgear, and under the circumstance, balancing resistance are inserted in the shortest length of the pilot, so that the relay tapping point is divided the whole secondary impedance of the two set of cities into equal portions. Those resistances are usually adjustable in order to obtain the exact balancing, and those resistances are called balancing resistance because the two pilot wires may not be equal in resistance value. Now, this is the limitation of this balancing or differential relays. It is a general practice to use neutralizing resistance in order to limit the destructive effect of earth fault currents. When the earth fault occurs near the neutral point, there may be insufficient voltage across the short-circuited portion to drive the necessary current around the fault circuit to operate the relays. So, due to when we near to the earth resistance or near to the neutral point, there may not be sufficient induced voltage. In that time, the relay cannot get the sufficient voltage to operate, and its usual practice protect only 80% of the winding by using this differential protection system. Now you can see here this is balancing resistance in order to balance the difference between the two, because why we added in this side on the CT2 side, because this is maybe found near to the switchgear, and most of the time these relay coils may be found around the switchgear or the near to the substations. So in this condition, these relays are close to the circuit breaker. Most of the times the circuit breaker is found around the switchgear, and this switchgear may be near far from the generator. So if this is far from the generator, there is high length in this side and CT1 side. So to compensate the resistance value of this wire, we may add some resistance value to balance the two resistances. This is the additional one to overcome the problem of unbalancing, and the other is remain as the same as to the previous one. This one the same as to this one. The only different here, you can see here there is no balancing resistance, but when you see this one, there is a balancing resistance. That's only different. Now let us see if there is some limitation on these types of differential relay. Let us see the modified one, which overcomes this limitation. Modified differential protection for alternators. In order to overcome the above limitation, a modified form of differential protection is used, in which setting of earth faults is reduced without impairing stability. So the modification affects only the relay connections and consists in connecting two relays for phase fault protection, and the third one is for earth fault protection only. In the previous one, you can see in the previous one we have the independent relay coils for each phases, but for this modify one, there is two uh, uh, phase voltage and one Rutherford relays. There are three relays, two phase elements PC and PA, and balancing resistance P are connected in star, and R is a relay which is represented by AR is connected between these star pointers and the fourth wire of circuit current pilot wire circuit. You can see this one. This is the modified version of the previous one. Here you can see this is PA and PC. Those are phase fault relays. They will act only for phase faults. And this one is BR is balancing resistance. This resistance, remember, this not relay, this resistance. And this one is the earth relay, which will trip only the earth fault, only the earth fault. What will, let us see the operation in such manner. Operation under normal operating conditions, the currents at the two ends of each stator winding will be equal. Therefore, there is a balanced circulating current in the phase pilot wire, and no current flows through the operating coil of the relay. Consequently, the relay remains inoperative. If an earth fault occurs on any one phase, R, Y, or B, the out of balance secondary current cities in that phase will flow through the earth relay ER and via pilot wires S1 and S1 or S2 to the neutral of the current transformer. This will cause the operation of the earth relay only. You can see here, if the fault is happen somewhere, some of the phases, it may be on phase R or phase Y and phase B, there is a current, there is earth relay here, earth relay. If the fault is happen on that way, so the current may flow in this way, in this direction. This is more sensitive than when you compare PC and PA relays. Is more sensitive, or when you say more sensitive, the pickup current is less than from the other. So in that time, if the earth fault is happen, their current will pass through this earth relay. In that condition, this earth relay will trip even if the fault is small. Now, if the phase fault is happen, there is no connection on this earth fault. For example, if this phase and this phase are shorted, the circulation current pass in such a way. For example, in this way, there is no any current which may pass through earth relay. So this earth relay will use only for earth forces. So if the fault occurs between two phases, that means the out of balance current will circulate around the two transform secondary via any two of the coil PA or BR or PC. Their pairing decided by the two phases. That means if the voltage pass through R and Y, so the current will circulate in BR and PC. If the voltage happen on Y and B, the current will circulate on PA and BR. And if the voltage happen between R and B, the current may circulate in PA and PC. So the passing of this circulation is depend on the voltage. But remember, this fault does not pass through the earth relay or air. Therefore, only the phase faults relay will operate in this phase fault conditions. Okay, balanced earth fault protection. In small size alternators or generators, the neutral end of the three-phase windings are often connected internally to a single terminal. Remember from the previous classes, those cities are connected in each phases. But in small generators, they may not be connected. Instead of here, they are connected by single city. So they are connected on single city. Therefore, it is possible to use it's not possible to use multiply circulating current principle because there is no facility for accommodating the necessary current transformers in the neutral connection of each phase winding. Under the circumstance, it's considered sufficient to provide protection against earth fault only by the use of balanced earth fault protection system. This system provides no protection against face-to-face faults unless and until they develop into earth fault, as most of them will. So until the other protection mechanism is developed, it cannot protect phase to phase faults, but they will protect or they are more secure for earth faults, only. As you can see here, this city is common for all. So this ideally the sum of those three currents becomes zero ideally, but practically it may be from a little bit from zero. And so if the sum of this current becomes ideally also zero, so the two currents, the sum of those three currents and this city becomes equal at normal condition. So this is the schematic arrangement of the balanced system or balanced earth fault protection. So schematic arrangement consists of three lines, current transformer, one mounted in each phase, and having the second line connecting parallel with that of single current transformer, and the conductor changing the start point of the alternator to earth. A relay is connected across a transformers, secondaries. The protection against earth fault is limited to the region between the neutral and the line current of the transformer. The line current of the transformer, you can see it. So if the sum of the two are balanced, there is no any current which pass through this relay. If the ground line fault F1 and F2 happen, the sum of those current cannot be equal from this one. In that time, the relay will get some current. If this current is greater than the pickup current of the relay coil, the relay becomes operative and the circuit breaker will break the condition. So under normal operating conditions, the current flowing in the alternator reduced, and hence the current flowing in the secondary line current transformer are to zero, and no current flows through the relay. Also, under those conditions, the current in the neutral wire is zero, and the secondary of the neutral can supply no current to the relay. If an earth fault develops at F2 external to the protective zone, you can see F2 is here is F2. Here is F2. If the fault is happen on this F2, you can see here if the fault is happen on F2 external to the protected zone, the sum of the current at the terminal of the alternator exactly equal to the current in the neutral connection, and hence no current flows through the relay coil. When an earth fault occurs at F1 or within the protected zone, those currents are no longer equal, and the differential can flow through the opening coil of the relay. Then the relay closes its contact to disconnect the alternator from the supply system. So this is based on the protection zone. If the fault is happened, there is no any significant difference on the relay coils, so this cannot trip the fault. But if the fault is happen on protective zone, that means in F1, it will protect automatically. Now let us see stator interturn protection. It is usually considered unnecessary to provide protection for interturn faults because they are invariably developed into other faults. For example, in some generators there will be only a single turn or single turn wire. In single turn generator, example large steam turbine generator, there is no necessity to protect against interturn fault because the internal protection is provided for multi-turn generators like hydroelectric generators. In hydro generators, they may have more than two windings. So those generators have double winding. For example, in a hydroelectric generator, each phase winding is divided into halves, two windings owing to the very heavy current which they have to carry. So the advantage may be taken of this necessity to protect internal fault on the same winding. You can see here is the in one winding there are double windings S1 and S2. So this is the two winding or double winding. Those two S1 and S2 are that in parallel way. Stator interturn protection. It is usually considered unnecessary to provide protection for interturn faults because they invariably develop into other faults. So, stator winding is required only for double or more than double uh, winding. So, single turn generator, example, large steam turbine generator, there is no necessity to protect against interturn fault. However, interturn protection is provided for multi-turn generators like hydroelectric generators. Those generators have double winding armatures. Example, each phase winding is divided into two halves owing to the very heavy currents which they have to carry. So advantages may be taken of this necessity to protect internal faults on the same winding. Look at this one. This one is the protection of hydro generator. This S1 and S2 may found in parallel. So there is the internal volt protection relay. R1 is required. So the two cities will compare the S1 and S2 windings. So if there is a fault happen on S1 or S2, there is now equal current on the two windings S1 and S2. Schematic arrangement of generally the circulating current and internal protection of three-phase double winding generator looks like this one. This is a general product. So this protection or this arrangement contains two things. The one is the differential protection. This one, this section. This one is similar to the previous one. Like this one is similar to this one, or you can see from the previous one. This one is like this one, or you can see from here this one like that one. They are already inverted. The only difference is that one. So this has two protection. The one is circulating current protection, and the other one is interturn. The interturn protection is this one. R1 is R1. It's the interturn relay, and RC is here. You can see RC is the circulating current relay. So the relay RC provide protection against phase to ground and phase to phase fault, whereas relay 1R provide protection against interturn. By the way, when we invert this one, you can get this one. Yeah, it is. So look at this one, and this one, they are connected inside. Now you can read here that the same to the previous differential current relay. You can see here is a common line, so these are connected to a common line like this one at the half of the pilot wire. So completely they are similar to the previous one, and this one is the internal coil, which is similar to this one. This is exactly the internal protection. So under normal conditions, the current in the stator winding S1 and S2 are equal, and no current flows through the relay R1. If a short circuit develops between adjacent turns, say we can say S1, if the fault interturn fault is happen or short circuit developed by adjacent two turns, say on this S1, the current in the stator winding S1 and S2 cannot be equal or no longer be equal. So the difference of the two currents may flow through the relay R1. Because if the two are equal, there is no current which passes across R1. But if the current in S1 and S2 cannot be equal, there is a differential current. This differential current will pass through R1. So the relay then closes to contact to clear the generator from the system. This is previous one. Now let us see some examples regarding the previous discussion. Let me see some examples. This is the first example.